In this video, we're going to look at conservation of linear momentum for a system of particles. And I'll consider the case in which there's no impulse. So if there is no impulse, and again, that would mean, there's no integral f dt, that's zero, or sometimes this would be f delta t. Then our conservation equation which look like this. If there's no f dt, that's going to be zero. So again, if there's no impulse, this reduces to m1 v1 equals m2 v2. And then if we have more than one particle, we'll have to sum these up. So we'll have, say, summation over the i's of mi1 vi1. There's lots of ways to do the notation. What I'm saying here is that this would be the first state. Say it's state one, we would sum up all the mv's for each particle that we have. So for 1, 2, 3, etc. So for an I is 1, 2, 3, up to however many particles we have, and do the same thing at state 2. So we'd have that. So this is called conservation of linear momentum. Now we set up here that there's no impulse. Now we may have internal impulses in some cases, maybe many cases, but they will cancel. Let me note that. We may have internal impulses. But these will cancel. So that's what we're going to be working with in this video. We're going to now look at this problem, F15-7. F15-7. The freight cars A and B have a mass of 20 megagrams and 50 megagrams respectively. Determine the velocity of A after collision if the cars collide and rebound, such that B moves to the right with a speed of 2 meters per second. If A and B are in contact for 0.5 seconds, find the average impulsive force which acts between them. And the one has a mass of 20 megagrams. 20,000 kilograms, and it's heading towards the other freight car, which has 15,000 kilograms. And is 1.5 meters per second. And so actually, it's asking for the impulse in between them, but we have to use the conservation momentum first to find the velocity. So we're told that after impact, car B moves to the right at 2 meters per second. That is, the velocity is going to be 2 meters per second out. So this after impact, we'll call that VB2. And again, if we call to the right positive, that one will be positive, then this one will be negative. So we use conservation of momentum. And so we'll have like MA1 VA1. So the initial mass times the initial velocity of car A plus the initial mass, initial velocity of B. And then that's going to equal to the final velocity of A times the final velocity, final mass of A, final mass of B, final velocity of B. So now we've been given most everything. We know the mass of A is 20,000 kilograms. Velocities to the right, we'll call to the right positive, so that'll be 3. The mass of B is 15,000. We'll call going to the left negative, so that'll be 1.5 meters per second. Then after impact, mass of A, of course, is still the same. And we don't know the velocity of A after the impact. And then the mass of B times the velocity B after impact. We said that was going to be, again, that's going to be positive 2 meters per second because we're calling to the right positive. So if you solve for velocity of A after impact, just put that all in your calculator, 375 meters per second. Since that's positive, we said to the right was positive, that means to the right. Now it's actually asking us for the impulse. Now again, when we look at the whole system, the two cars together, there is no impulse because it cancels out. But if you look at either one of the cars, you can see what the impulse is on that particular car, and you can use either car. I'll show you. You will get the same answer both ways. So let's look at the impulse. So consider, let's say, car B before and after collision. And again, for this, we're going to have to use impulse and momentum. We'll have to use the stuff from the previous chapter, the previous section, which is, so the math, again, just looking at B, the velocity of B before impact plus our impulse. Now it's asking for the average impulse, so we can just use FDT. We don't actually have to integrate anything. So F delta T B2, P2 like this. And so we'll see what happened again before impact. It was moving at 1.5 meters per second to the left. And it tells us that they're in contact for 0.5 seconds. So that's how long the impulse would be. So 0.5 seconds. And then it's going to be equal to 15,000. And then the final velocity of B we were given was 2. So our only unknown is F. If you put this in your calculator, you would get F equals 105,000 newtons. Now, just to show that we could have used either car to analyze this, so we can check this. So consider car A. Car A before and after. And so, again, do MA1, VA1 plus F delta T equals MA2, VA2. And once again, it's going to be 20,000 times 3 meters per second plus F delta T. We were told it's going to be in 0.5 seconds. And we're told, or we actually calculated that the final velocity of A was 0.375 meters per second. And if we put all this in our calculator, we get a negative 105 newtons, like that. So we could have used either one. We're just looking for the impulse or the force between the two cars. So we got, by using car B, we got 105,000. And for car A, we got 105,000 negative. So got the same thing. So could do either way. Next, we're going to look at F15-9. We have a 5 kilogram block that has an initial speed of 5 meters per second. And it slides down a smooth ramp. Of course, that implies no friction. After which it collides with a stationary block B of mass 8 kilograms. If the two blocks couple together after collision, determine their common velocity immediately after collision. And so we have this package sliding down. It's 5 meters per second. Starts at A. And so it weighs 5 kilograms. And we're told that this is 1.5 meters here. And so we're asked to determine their common velocity immediately after collision. So we're going to have this block come down here, hit block B, and see what their velocity is. Now we're going to have to find out, obviously, we need to know the velocity of block A when just before it impacts B. So let's see, how could we do that? Does anyone have an idea how you would find that from stuff we did previously?
Use conservation of energy.
Good. Yeah, conservation of energy would work. Good. We can use conservation of energy. And again, because we have a smooth surface, then that's real easy to apply. And remember that was T1 V1 equal T2 V2. And you remember this kinetic energy here that is going to be let me write it, 1/2 mv1 squared plus, and then remember the potential energy could be from the spring or from it being at a certain height. So we'll have to identify a datum line. Let me call this the datum line here. Call that the datum line right there. Again, you could use this or this. I'll just pick that. So again, remember we have the potential energy is going to be the weight times y, where y is the distance to the datum line. And then on the other side, 1/2 mv2 squared, once again, plus the weight times y. We should maybe mark one of these. I don't know, maybe mark one of them y1 and y2 just to distinguish them. Now, since we're starting at the datum line, this y1 is going to be 0. And then again, the mass is going to be 1/2, 5 kilograms. It's starting at 5 meters per second. Then on the right-hand side, 1/2, 5. And the final velocity, we don't know. And then once it gets down to B, our mass will be below the datum line, so it's going to make it negative. Again, remember that's because we're below the datum line. And the mass is 5 times, excuse me, the weight is 5 times 9.81. And then it's 1.5 meters below the datum line. So that's all we need, huh? So if you put that on your calculator, you get W2 is 7.38 meters per second, just as A impacts B. So now, once they impact, then we have to use conservation momentum. So again, now the two blocks are together here. This is B, this is A, and they're coming in contact. So if we use conservation of momentum, MA1 VA1 plus MB1 VB1. This would be their condition just before impact. Then after impact, they're going to be together, so the mass is going to be summed, huh? So it's going to be mass A plus mass B, like that,
times maybe, what do you want to call it? Maybe the final velocity. So before they were separate, then once they come in contact, they're going to be together here, and they're going to have like one velocity they're moving along. Once again, B is stationary at the beginning, so it's going to be 0 to start with. So A is 5 kilograms times 7.38 equal 5 plus 8 times the final velocity. Then the final velocity just after impact is 2.84 meters per second.
Next, we're going to look at this problem F15-11. F15-11. Blocks A and B have a mass of 15 kilograms and 10 kilograms respectively. If A is stationary and B has a velocity of 15 meters per second just before collision, and the blocks coupled together after impact, determine the maximum compression of the spring.
So we have a spring that's at 10,000 Newton meters, and block B is heading for block A. And so this is similar to the problems you had before, except remember before we had a block heading towards the spring, but we didn't have another block here. So in other words, all we had to do is see what would happen when this block B hit the spring. But because we have another mass here, a second mass, we're going to need conservation of momentum. So this is we solve it almost like we did previously, except we need conservation momentum to find the velocity after impact. So yeah, just just after impact. So use conservation momentum. So it's going to be MA1 VA1 plus MB1 VB1. Then after they impact, they move together. So it's going to be mass A plus mass B times the velocity after impact. I don't know what you want to call it. Let me call it just F. So after impact. So again, to start with, A is motionless, so it's going to be 0. So we're going to have 10 times 15 on the left. And then our mass in the ray is 15 plus 10 is VF final. And that's, you can see that's easily, the velocity after impact is going to be 6 meters per second after impact. So now that we found that, this becomes a problem that you did in the last chapter, like on the last exam. And once again, we can use conservation of momentum. Because what we have now is this is something contacting the spring. So, and these kind of move together now, these two masses to become one after impact. And so, so use a conservation of energy. Again, remember that T1 V1 equals T2 V2. And once again, it's 1/2 MV uh, MV, what do you want to call this? MV squared before impact, or just after impact, I should say, just after impact. And now for our potential energy, again, there's no change in elevation, but we do have a spring. So we're going to have to put in the potential energy for spring. So this equals 1/2 M after it stops on the right hand side. I'm going to call this, I don't know what kind of subscripts you want to use here, because we already used F. And then once again, the spring over here, like this. So again, this is the spring, and S is 0 before the spring compresses. So this is going to be 0 just as they're coming in contact. There's going to be no compression of the spring. And then the velocity to start with, we just calculated that. Now they're moving together, A and B are moving as though they're one. So it's going to be the total mass times the velocity squared, again, plus 0 here. Then on the right-hand side, we're looking for the maximum deflection. So that's going to be when the velocity is 0. So this is going to be 0 here. So that first term is 0. And then this is going to be 1/2. And our spring constant was at 10,000 newtons per meter times S squared. And so if you put that all in your calculator, you'll find that S is 0.3 meters.
Next, we're going to look at this problem. This is a fairly simple problem. This is 15-35. The 5 megagram bus is traveling to the right at 20 meters per second. Meanwhile, a 2 megagram car is traveling at 15 meters per second, also to the right. If vehicles crash and become entangled, determine their common velocity just after collision. Assume that the vehicles are free to roll during collision.
As I say, I like to change if it's in megagrams. I always change it to kilograms. A lot easier to work with. So it's coming in this direction. The bus is 20 meters per second. And the car is 15 meters per second. And so it wants to know the velocity just after collision. And so that's, again, just conservation of momentum. And so M bus, V bus plus M car, V car Again, when they impact, they're going to move as one. So we use the total mass of the two. So then the final velocity. And so it's going to be 5,000 times 20 plus 2,000 times 15, 5,000 plus 2,000, the final. So yeah, all you have to do is plug in the numbers. The final around 18.57 or 18.6 meters per second.
Next, let's take a look at this problem. This is 15-36. 15-36. The 50-kilogram boy jumps on the 5-kilogram skateboard with a horizontal velocity of 5 meters per second. In other words, the boy is moving at 5 meters per second when he jumps on the skateboard. Determine the distance s the boy reaches up the inclined plane before momentarily coming to rest. Neglect the skateboard's rolling resistance.
And he weighs 50 kilograms. And the skateboard is 5 kilograms. And the question is how far, so he jumps on the skateboard and goes up this smooth incline here. And the question is how high will he end up? So once again, this almost sounds like a problem you had before. Remember, if you had something going at a certain velocity and you want to know how high it went, in fact, on the last exam, I guess you had one like this, and you needed to know, like, what velocity it was at this point before you could find here. Now, before it was usually given to you, but now we have to find that. So you can see we can use conservation of momentum to see how high it's going to go. Well, excuse me, conservation of energy to see how high it's going to go. But first, we have to use conservation momentum to see his starting velocity. So we'll use that. So conservation momentum again. And so we have, say at the beginning, the boy, velocity of boy, and then plus this skateboard, velocity of skateboard before he jumps on. And then afterward, they're going to move together. So again, I don't know what you want to call. I would just call it VF or V final, something like that. So once again, the first part's pretty easy. Again, the skateboard's not moving to start with, so it's going to be 0. And then the boy's 50 kilograms, and he's moving at 5 meters per second. After he jumps on the skateboard, the two are going to move together. And if you solve for the velocity, 4.55 meters per second. And since it's smooth, he's going to maintain that speed until he gets up the incline. So you can think of this as his velocity at the bottom of the incline. And so now it just becomes a problem like you did for the last exam. He's down at the bottom here, how high he can go. Once again, we use conservation of energy. So notice how many times we use conservation of energy in these problems. Again, usually these are problems that we could have solved previously, but we were missing some information. then use conservation momentum to get the information. In this case, the velocity at the bottom of the incline. So do conservation of energy. So think of what we have. So we have this incline here, and he's at the bottom here. The question is, how high can he get? And it's actually how far of a distance along the incline. But we can first do it using the height, huh? Because we know how to do that using conservation of energy. So let's just call this a height here. So we'll first find that then. So we want to find that height. And again, we'll name this the datum line down here, huh? We can name this the datum. So if we use conservation of energy, T1, V1, T2, V2, 1/2 MV1 squared plus, again, our weight times our distance to the datum, 1/2 MV2 squared plus our weight times the, or actually in this case, when he gets us to his height, h, that'll be his distance from the datum line, huh? So in other words, when he gets up here, that's what we're looking for. We want to see what this h is. So we want to know what happens when he gets up here to this height. So we'll use h for that distance from the datum line. So once again, he's the two together. It's going to be 50 plus 5, the total mass that the kid in the skateboard. 4.55 squared, we found that a minute ago, is the velocity. And again, he's at the datum line, so at the beginning that's going to be 0 because he's at the datum line. And then for the next part, we want to know his highest point, and that's going to be the point where he goes up and stops momentarily. So the velocity there, of course, is going to be 0. And then his weight, he'll be above the datum line, so it's going to be positive. So it's going to be the 55 times 9.81 times the height. So again, just using the basic conservation of energy. And solve for h. And we get 1.055 meters. Now, the only thing is they asked for the distance along the incline, so we're going to have to find that. So in other words, if you look at the picture, they're asking, like, say, for this distance, S, to where he got to his maximum height, and we found H, which is 1.055 meters. So we found this distance, H, here. And so we can just use trig, how we can just say that, let's see, if this is 30 degrees, and usually we're finding the side. This time we have to find the hypotenuse. So I guess that would be the opposite over the sine, huh? So the distance S is going to be opposite, which is 1.055 divided by the sine of 30 degrees. And when you put that in your calculator, you get around 2.11 meters.
In this next problem is going to be 15-39. 15-39. It says a ballistic pendulum consists of a 4-kilogram wooden block originally at rest. That is, the theta is 0 degrees. When a 2-gram bullet strikes and becomes embedded in it, it is observed that the block swings upward to a maximum angle of theta equals 6 degrees. estimate the speed of the bullet. So we're going to have to sort of work backwards, and we're going to have to start by looking at the fact that the bullet gets embedded and then it has the block to a maximum angle of 6 degrees. That means the block will have raised just a bit, as you can see from the picture, and the bullet would have gone up just a bit.
So let's think of the plan here. First, find velocity of the block with the bullet inside. We're going to have to find that first. And then, and again, we can do this, again, since this just has the block and the bullet together, and we know how much it moved 6 degrees, which is going to convert to a height. So we can use conservation of energy for that part. And then we can go back and use, then find the velocity of the bullet. So we have to kind of work backwards on this one. So this would be step 1 and step 2, like that. So, so first of all, I guess to do step 1, we're gonna have to figure out how much the block has raised up. So, how much did the block raise? And so just have to use some basic, just some basic geometry. So in other words, if it's 6 degrees, so it was originally, like say, if you look at those connections, if it was originally down here, if this was like our 1.25 distance here, so like this is 1.25 here, then the block raised this much. So if we can find this distance here, if we can find this height here, we can find out how much the block raised. So if you look at that picture, if you know what that is, then that's going to be the height that it raised there. Remember, this whole distance is 1.25. So now this side over here, right here, if this is 6 degrees, this is going to be 1.25 cos of 6 degrees, huh? 1.25 cos of 6, which is 1.243 meters. So that means then the height that it raised up was going to be the original 1.25 minus 1.243. That's going to be like how much the block went up. Once again, if you kind of look at your picture, you know, what's happened is that this has moved from here to here. So if you can find that distance there, which we have here, that's going to be the increase in height. And that's going to be, when you subtract that, 0.0068 meters. So now, again, so we can use, so now we have a difference from beginning, ending height. We use conservation of energy, huh? Conservation of energy going to tell us the velocity of the block and the bullet together. Again, that's going to be, I'll write this kind of fast since we don't have a lot of time left. And once again, let's call this point down here the datum line. Let's do the starting point as our datum. Use our starting point like as our datum line down here. When, in other words, when the block is just sitting with no angle. So call that our datum, and then equal 1/2 mv2 squared plus w. And again, after the impact, our h is going to be the distance from the datum line. So we'll use that as our h. So just plug everything in. So it's going to be 1/2, and then the mass of the block plus the mass of the bullet. And then originally it's at the datum line, that's going to be 0. And then when it says maximum height, the velocity is going to be 0. And then plus the weight, which is at 4.002 times 9.81. And we calculated what our height was, 0.0068 was our height. And if you put that all in your calculator, you get a velocity of 367 meters per second. And that was bullet plus block after impact. Then finally, to find out what the velocity before impact was, use conservation of momentum. And again, that's pretty straightforward. It's going to be m of the bullet, velocity of the bullet. Again, this just before impact, the block will be separate. And then the final, so again, this is going to be like the bullet plus block, excuse me, m block times our final velocity, or our total or final velocity. And we know what that was. We know what the velocity is after impact. We already found that, so we can just plug that in. So again, over here, the bullet was 0.002 kilograms. The velocity of the bullet, don't know. And again, before impact, the block was motionless. 4 plus 0.002, 9.81. And we know, again, we calculated the velocity of those two together. And so the velocity of the bullet, you put that on your calculator, you get like 733.4 meters per second. See if that'll make sense. Any questions on that? Notice, again, these problems, they're pretty low. You just kind of follow them step by step and just apply the basic principles, and they work out pretty nicely. If no questions, I'll see you on